Hello and welcome to the video where we're going to do some examples from the content we did on Monday. So find each of the following antiderivatives. The first one we have is 2 sine x dx. And for this one, the only thing we would really need to notice is that we've got this 2, which is a coefficient. So technically we could write this as 2 times the integral of sine of x dx, which is equal to this guy. Oh, that was not a good little squiggly. The integral of sine is negative cosine of x plus c. Because technically we are multiplying this by 2, we would be left with negative 2 cosine of x plus c. And I think someone had asked this during class. I don't really know if I went over it with everyone, but yes, we would be distributing this 2 to the c, so we could write that as 2c, but 2 times a constant is still just a constant. So the second one, unfortunately, isn't exactly one of our original functions. So we have to do a little bit of work here, and that work involves simplifying our trig identities. So I look at this and I think, well, I could write this as sine x over cosine of x times 1 over cosine of x. Sine over cosine is really tangent. 1 over cosine is really secant. And now look what we have. We've got secant times tangent, or tangent times secant, right? It's the same thing. So the integral of tangent secant, or the antiderivative of tangent secant, is secant of x. Oops. With respect to x, or not with respect to x, I'm sorry, secant of x plus c. Next up, we want to look at our natural log and exponential functions. So the antiderivative of 5e to the x, well, the antiderivative of e to the x is just e to the x, but we have this 5 out front, so we can multiply that by 5 plus c. Pretty boring. The antiderivative of 6 to the x, well, this is this property right here, 1 over the natural log of 6 times 6 to the x power plus c. For the next one, we are looking at the antiderivative of 5 over x dx. And for this one, it would probably be good to, again, note that this is the same as the integral of 5 times 1 over x dx, which is really the same as 5 times the integral of 1 over x, because we can pull out that coefficient. And so the integral, the antiderivative of 1 over x, is the natural log of the absolute value of x plus c, and then we got to multiply by 5. So 5 times the natural log of x plus c. And last but not least, we've got our definite integrals, which is combining two pieces now. It's going to look at the integral and taking an antiderivative, but then also looking at the bounds. So for b, we start by finding the antiderivative of x squared, which is going to be 1/3 x cubed. This is really x to the 1/2. So the antiderivative of that would be x to the 3/2. And up front, we would put this as 2/3. And we are going to evaluate this from 1 to 0. When I say evaluate, that means plug in the upper bound. So 1/3 times 1 cubed plus 2/3 times 1 to the 3/2. Plug in the upper bound and subtract from it the lower bound. So I'm going to move this all over because we need a little more space. Although maybe you're looking at this thinking we don't really need space, but for emphasis, I'll put it 1/3 times 0 cubed plus 2/3 times 0 to the 3/2. Sorry, that's all squished there. It doesn't really matter though, because we have 0 plus 0. This piece is just 0. 1 cubed is just 1. 1 to the 3/2 is just 1. So I have 1/3 plus 2/3. I get 1. This would be a problem that you could check using your derivative, or excuse me, antiderivative on the calculator. So math, option 9, function integral. For C, I apologize, there is a slight typo. We are actually going to look at this one with the bounds from -π/4 to +π/4. So the antiderivative of 2 secant squared theta d theta, well, I know the integral of secant squared is tangent of theta. I know I can take this coefficient and tag it on after. So we are evaluating 2 tangent of theta from -π/4 to +π/4. I could write that as 2 tangent of π/4 minus 2 tangent of -π/4. Got to think about your unit circle. I know that π/4 is right here, square root of 2/2, square root of 2/2. So that means tangent of π/4 is 1. So I would have 2 times 1 minus -π/4 is down here. We have the same point except for positive square root of 2/2, negative square root of 2/2. That means tangent of -π/4 is a -1, meaning I have 2 plus 2, 4. I'm going to pause the video and just make this look a little nicer. All right, I look at D and I think we have to do a little bit of simplification first. So I would start by breaking this up into 1 over the square root of t minus the square root of t over the square root of t dt. We're still going from 4 to 9, and I would write that as the integral from 4 to 9 of t to the -1/2 minus 1, which then I would take the antiderivative and I would get 2t to the 1/2 minus t. We are evaluating that from 4 to 9. So I would have 2 times 9 to the 1/2 minus 9 minus 2 times 4 to the 1/2 minus 4. And when I simplify this, I get -3. Two more. E is the integral of e to the x evaluated from 0 to the natural log of 5. This was an easy one. The integral of e to the x is just, oh gosh, e to the x. I don't know what that is. I'm evaluating it from 0 to the natural log of 5, which means I have e to the natural log of 5 minus e to the 0 power. Well, anything to the 0 power is just 1. So I know this second piece is 1. If you remember your properties of logarithms, e and natural log have the same base, which means e to the natural log of 5 would just be 5. 5 minus 1 is 4. And last but not least, f. I'm going to actually pull this down here just because I want a little more space. The integral from 1 to e squared of 3 over x dx. I start by thinking, well, this is really 3 times 1 over x, which means the antiderivative would be 3 natural log of the absolute value of x. We are evaluating this from 1 to e squared. So I plug in my upper bound, 3 times the natural log of e squared minus 3 times the natural log of 1. Again, you need to know your properties of logs. Natural log of 1 is 0, so this is just 0. Here, I would start by taking this, pulling it out front. So I have 6 times the natural log of e. The natural log of e is just 1. My final answer is 6. All right, have a good rest of your day.